talk about what happens when we get infinity involved in these limits. And there's a few different, there's positive and negative infinities, and the definition changes a little bit because infinity is not an actual number. So here, let's look at what happens if the limit is equal to infinity. And then I realize we're saying that means the limit does not exist, but sometimes we can say the limit equals infinity. For example, if we have a vertical asymptote and we're looking at what's happening near there. So let's say f is a function, again, defined on an open interval that contains this number c, except for possibly it's not defined at c itself. So we'll say the limit of f of x as x approaches c is positive infinity, and write it in this way. If for every positive number capital M, there is a number delta that's greater than 0, such that the y value, f of x, is greater than capital M whenever x satisfies the fact that x and c are less than delta away from each other. So whenever those x values are really close to c, then the y values are bigger than some capital M. And I've got a Desmos file that you can look at if you want to, and I'll look at it right now. So here I've got a function 10 over x minus 3 squared, and it looks like it has a vertical asymptote at 3, and I'm interested in what's the limit as x approaches 3, so that's why I've got c equals 3 here. The limit definition says that the limit is infinity if for every capital M I pick, there's a certain delta, so that whenever x is within this delta band, the y values are greater than capital M. So the way that I've got this set up is my M changes and lowers this blue, the bottom of this blue part, and delta is again centered on the c value. So c is 3, and so when delta is equal to 1, I've got my delta neighborhood going from 2 to 4. Okay, so if I want to see that when are the numbers greater than 100, then I need to shrink my delta down to about, there it turned green, about 0.306. Let's just say 0.3. I like that one better. So when delta is 0.3, all of the y values within there are greater than 100. But let's pick a bigger m value, because the definition said for every positive number m. So let's pick a bigger number, maybe 500. So now I'm saying, is there any sort of delta I can get so that those numbers within delta of 3 are greater than 500? It looks like 0.14 would work. What about if I choose a m of 1,000? This delta doesn't work, but if I shrink delta down a little bit, maybe to 0.09, then all of the x values in this delta neighborhood of 3 give me y values that are bigger than 1,000. So the idea is, can we keep making this bigger and bigger? So if I look at 2,000, can I shrink my delta down? Looks like yes, I can. 0.07 would give me y values that are greater than 2,000. So that's the idea, if I keep getting bigger and bigger and bigger. Related to that is what happens when the limit is equal to negative infinity. So we can say the limit of f of x as x approaches c is negative infinity, and write the statement like here. If for every negative number n, there's this delta that's greater than 0, so that the y value is less than n whenever x satisfies this statement that the distance between x and c is between 0 and delta. Notice I'm saying 0 is less than that because I don't want it less than or equal to. I don't want x to actually equal c. I want it to just get really, really close. So I've got another Desmos file here that looks at that one, and I put the link on the PowerPoint slide. The function is 250 minus 50 over x to the fourth. It looks like the y-axis x equals 0 is a a vertical asymptote. And so if I shrink down a delta so that, there we go, so that the number, all of the y values are less than 100 here, the delta of 0.75 works. If I shrink that, not shrink that down, if I make n even more negative, maybe negative 300, I want to find a neighborhood around 0. There we go. Delta of 0.54. This goes from negative 0.54 to positive 0.54. That's hard to see. Let me make it 0.5. There we go. So this goes from negative 0.5 to positive 0.5. And it says anytime the x's are within that range, the y values are going to be less than negative 300. And I could just keep picking smaller and smaller numbers, more and more negative, and say, could I find a delta that works? Yep, I can. And if I can always do that, we say that the limit is approaching negative infinity. There's two other things we need to look at. What happens as we're looking at limits when x approaches infinity, or as x approaches negative infinity. So if f is a function that's defined on some interval from a real number up to infinity, we say the limit of f of x as x approaches positive infinity is L. If for every number epsilon greater than 0, there's a capital N such that the distance between the y value and L is less than epsilon for all x values that are bigger than that capital N. Here's a Desmos file for you to look at here. My function is 1 over x. I've chosen epsilon is 1/2. And it looks like whenever, this is already green, let me make it smaller so it's not. When n is 1, there are some y values that are outside of this epsilon band. And I'm thinking the limit is 0 for that. If I make n larger, like n equals 3, 1/3, 1/4, 1/5, any of these numbers for after, any of these x values after 3 would give me 1 over that number is less than 0.5. So now I pick smaller epsilon values, maybe 0.25, and now I need to pick a larger n, and whenever x is bigger than that capital N, the y values are within this epsilon band of the limit, which I think is 0. Make a smaller epsilon band, 0.1. Then I think at 1/10, that at n equals 10, that would be 1/10. So I could make it even smaller, or make n even larger, and that would shrink the values even smaller. So the idea is, if we can keep shrinking this down, can I keep finding numbers that are, I can't even see that, it's off the screen. Let me make my x-axis go to maybe 200. There we go. So around, it looks like 34. Once x gets bigger than 34, the y values are within that tiny epsilon band there. One more definition, as x approaches negative infinity. If the function is defined on some interval from negative infinity up to a real number, we say the limit of f of x as x approaches negative infinity is L. If for every number epsilon greater than 0, there's a number n such that the distance between f of x and L is less than epsilon for all of the x's that are less than n. There's a Desmos file here, and I've got the same function 1 over x, but now I'm wondering what's happening as x goes to negative infinity. I think the limit is 0. If you thought the limit was 1, then you could move that up to there, but I don't think that's the limit. I think the limit is 0. And as epsilon is 0.5 there, if I, looks like if I make n negative 3, whenever x is less than negative 3, the y values are within 1/2 of a unit of 0, so they're within the epsilon band. Then if I shrink epsilon down to maybe 0.2, I have to find another n right there. And looks like, n equals -6 works for that. So whenever n's are less than -6, the y values are within that epsilon band. So that's Desmos helping us get a look at the formal definition and try to understand what's going on. In the next video, I'm going to show you how to actually calculate and find the delta for any given epsilon.